Hello everyone. We'll wait for some 5 minutes to let everyone join and then we'll start the session. I hope everybody can see my screen. Can someone confirm?
Yes, ma'am.
Okay. We'll start the session. Okay. So welcome everyone to the fourth TA session for Drug Delivery Principles in Engineering. And today also we'll discuss the topics that were discussed in the previous week as well as some previous year assignment questions. So in the last week, the topics that were covered mostly were based on nano and microparticles, their properties, synthesis, method of synthesis, etc. And under this nano and microparticles, liposomes were also included. So nanoparticles are basically particles up to 100 nanometer size and from 1 to 100 nanometers, and microparticles are particles from 100 nanometer to 1 micrometer. So based on these and then the synthesis of these particles were discussed using either single emulsion method or double emulsion method. Single emulsion method is basically a solvent evaporation method for mostly hydrophobic drugs, wherein there is oil and water emulsion. So you put your drug in the polymer solution in the organic phase, and then use the water phase to create an emulsion, and let the polymer in the stirrer to let the organic solvent evaporate, and that's how it will form your small particles. Based on the homogenization speed to form these emulsions, you can use high speed homogenizer by mechanical disruption. Basically, you are creating an emulsion. So based on the speed, you can either make nano or micro. The higher the speed, the more smaller droplets will be formed because of the high speed of these homogenizer. So and then there is another method called the double emulsion method. So this allows encapsulation of both hydrophilic and hydrophobic drugs together, because in water you can water and put your drug in water, and then there will be a covering layer of oil and then another layer of water. So that's how it creates a hollow cavity between the two water layers, wherein your hydrophobic drugs can be encapsulated or your hydrophilic drugs could be encapsulated in the inner water layer. And liposomes are basically your lipids, these microparticles or nanoparticles based on these lipid membranes. And here also you can either encapsulate your hydrophilic drug in between the lipid layer, or hydrophobic drug in between the lipid layer, or the hydrophilic drug inside the empty core. So based on this, like these nanoparticles, microparticles, and liposomes, these are used for different drug delivery methods for different diseases. Now we'll try to solve few previous year assignment questions based on this. I hope I'm still audible.
Yes, ma'am.
Okay. Okay, so this is the first question. Which of the following particles will be cleared the fastest by kidney? You have to select two correct answers here. Let me know what you think the answer is, and then we'll discuss. Okay, 1 and 5. Anybody else would like to answer? Which of the following particles will be cleared fastest by kidney? You have to select two correct answers here. and positively charged. Okay. Yes, both of you are correct. It will be positively charged and the cationic particles. So this kidney has this glomerular basement membrane, which is basically negatively charged. So the negatively charged or anionic and neutral particles, basically anionic and negatively charged, will be repelled, and then the neutral particles will be slightly affected with it, but the positively charged and the cationic particles will interact with this negatively charged membrane and get cleared out fastest by the kidney. So the correct answer will be option 1 and option 3, positively charged and cationic. And then the anionic particles will come next, and sorry, the neutral particles will come next, and then the negatively charged or the anionic particles will come. Okay, moving on to the next question. What do you understand by the term encapsulation efficiency? Among these options, which one best describes the encapsulation efficiency? Option 3. Option 3, option 2. Okay. Yeah, so here the correct answer would be option 3, the percentage of the starting drug amount that is captured in the final or the finished polymeric particles. Okay, moving on to the next question. In single emulsion solvent evaporation method of particle synthesis, what is the use of surfactants? You have to select one correct option here. Anybody answered? hope I'm still audible to everyone. Okay. Yes, among these options, which of the option do you think is mentions the use of surfactants during single emulsion solvent evaporation method? Anybody would like to answer? Option 2, option 3. Okay. Okay, so the correct answer is option 2, to reduce the surface tension. So in single emulsion method, the evaporation method of the particle synthesis, the surfactants, as you know, surfactants have both hydrophilic and hydrophobic ends, right? So, and we are using two different phases, the oil phase and the water phase. And now that you have created an emulsion, there is small droplets of the oil phase in the water phase. And to stabilize this oil phase, we use this surfactants. They'll uh, interact with the droplets of this oil phase and stabilize them in a medium of the water phase by reducing the surface tension. Okay, moving on to the next question. What are the disadvantages of using emulsion based methods for synthesizing nanoparticles? You have to select two correct options here. Anybody would like to answer? What are the disadvantages of using the emulsion based methods for synthesizing the nanoparticles? 1 and 8. Okay. Yes, the correct answer would be 1 and 8. So high polydispersity and difficult to synthesize particles below 150 nanometer. High polydispersity here, it means there will be a higher range of particles based on the size. Let's say if you want to make 500 nanometer, then you'll get a range from 100 nanometer to 1 micrometer. That's a huge range or huge polydispersity index, and there will be lot different sizes of the particles with not a very narrow range that you would like when making particles. You would like a narrower range of these similar kind of particles if you want to use further. So that is one of the challenge in using the single emulsion, using the emulsion based methods for synthesizing the nanoparticles. Also, it is difficult to synthesize particles below 150 nanometer. Now, moving on to the next question. Consider we are encapsulating DNA plasmid along with a hydrophobic drug, let's say rapamycin, in PLGA microspheres. Choose the best choice of synthesis that would have higher bioavailability of both. Let me know what you think the correct answer is. You have to select one best choice for synthesis of particles wherein you can encapsulate both DNA plasmid along with hydrophobic drug rapamycin. Options are single emulsion with DNA and rapamycin encapsulated together with PEG on the outside, single emulsion with rapamycin in the matrix and DNA added after formation that diffuses in the microsphere, or double emulsion with rapamycin in the inner water phase and DNA arranged on the surface of PLGA, double emulsion with DNA in inner aqueous phase and rapamycin in the PLGA matrix. Which of these do you think is the best choice? Anybody would like to answer? Option 4. Okay. Yes, all of you are correct. Option 4 will be the correct answer. Double emulsion with DNA in inner aqueous phase and rapamycin in the PLGA matrix. As I said before, we can make a double emulsion particles with inner water phase, a middle layer of the hydrophobic or the a hydrophobic phase with the polymer phase, and then another outer layer with the water that will be in touch with the water. So the inner, during the formation of the double emulsion particles, the DNA can be encapsulated in the inner aqueous phase, and the hydrophobic drug can be encapsulated in the or rapamycin can be encapsulated in the polymer phase in the during the organic uh, when solubilizing this polymer in the organic solution. Okay, moving on to the next question. Select the correct option here. You have to select two correct options here. Nanoparticles with hydrodynamic diameter 6 to 100 nanometer can traverse through the glomerular filtration membrane. Second option, proton sponge effect is used to help particles escape degradation from lysosomes. Third option, endosomal compartments have pH in the basic range. Or fourth option, which is microparticles formulation has the potential to improve the shelf life of drugs. Anybody would like to answer? Is 2 and 4 the answers for this question you guys have written, is it? Okay, the correct statements here would be option 2 and 4. Proton sponge effect is used to help particles escape degradation from lysosomes, and microparticles formulation has potential to improve the shelf life of drugs. The endosomal compartments, option 3, have endosomal compartments have pH in the basic range is false, they have in the acidic range. And nanoparticles with hydrodynamic nanometer of 6 to 100 cannot traverse through the glomerular filtration membrane. Moving on to the next question. Liposomes are made of phospholipid bilayers and membrane fluidity is important for drugs to pass through them. Select the correct option about membrane fluidity. It doesn't depend on the cholesterol content of the bilayer. As temperature increases, fluidity increases. It is independent of the length of fatty acid tail, or as temperature increases, fluidity increases. Option 2. Okay. Yes, all of you are correct. Option 2 will be the correct answer here. As temperature increases, the fluidity increases. Fluidity of these membrane bilayer, phospholipid bilayer, and membrane fluidity increases. Moving on to the next question. Which one of these is not an advantage of nano and microparticles? Options are injectable, no need for surgical implantation, can elicit inflammatory reactions in host, possible way of delivering large hydrophilic molecules inside cells, particles can be adapted for targeted delivery to cells and tissues, or improving the stability of the drug in vivo. which one of these do you think is not an advantage of nano and microparticles, or is a disadvantage of nano and microparticles? Option 2. Okay. Yes, all of you are correct. Option 2, or can elicit an inflammatory reactions in host, is not an advantage or a disadvantage of nano and microparticles. You would not want inflammatory reactions with your nano and microparticles. Okay, moving on to the next question. Which one of the following parameters does not affect microparticle synthesis using double emulsion method? Options are polymer type and molecular weight, polymer concentration in the oil phase, organic solvent and polymer solubility, type and amount of surfactant in the external phase, internal aqueous phase or organic solvent ratio, rate of stirring and type of mechanical force, or none of the above. Option 7. Okay. Yes, the correct answer is option 7. All of these parameters in practicality, all of these methods affect the microparticle synthesis while using the double emulsion method. So the correct answer is none of the above. Okay, that was all the questions we had for today. If you have any doubts in any of the questions or any other doubts in general, you can ask, or we can close this session here. Please let me know if there are any doubts. Okay, you want to know about the difference between encapsulation efficiency and loading level calculation, right? Okay. Second. So encapsulation efficiency is basically how much amount of drug you started with and what is the amount that you have captured in the final amount of particles. But loading amount is basically how much amount of drug is retained as compared to the polymeric particles, the amount of polymeric particles. Okay, I am not sure if that is clear. I'll try to give one example. Okay, let's say you are making a you are using a 200 mg of polymer, and suppose you loaded 20 mg of the drug. Now the final amount that you recovered after analysis, uh, you get some 180 mg of the total particles, and when you analyze the drug amount, you found that, let's say, 12 mg of the drug is retained in there, right? So if you want to calculate the encapsulation efficiency, it will be basically the amount of drug encapsulated, which is here in this case will be 12 mg, for the same amount of drug. So initially you expected you would use some amount of these polymer, a consistent amount of this polymer to get the encapsulation efficiency, right? You are not using the entire 180 mg. Let's say you used some 1 mg per ml of the drug. So you need to calculate in 1 mg how much of these 20 mg would have been there, and now in 1 mg how much of this 12 mg is there. But to simplify it, we would just say 12 mg is the final amount of drug that is remaining, and the expected amount was your full amount, which is 20 mg. So the encapsulation efficiency percentage will be just 12 by 20 into 100%. This will give you your encapsulation efficiency. But the loading efficiency, or the drug loading amount, the loading amount would be this 12 mg that is retained with you, this 12 mg that is retained, and how much amount of particles you were able to recover from it. So this 12 mg in 180 mg of polymer is your final loading amount of the drug. This will give you a drug loading percentage. I hope that was clear. Okay. Any other doubts?